Uh, the chapter 10 and 11 homework will be due on the 4th. Is that right? No, those days are off by a day, I think. This should be 3, 8, and 10. Yeah. Sorry. Those were from last year. Not very different. So chapter 10 and 11 homework is due on the 3rd. The review of chapter 10 and 11 and 13 will be on the 8th, and the exam on chapters 10, 11, and 13 will be on the 10th. If you need to take the exam early, let me know. I will make sure it's ready. So here is an example of zero torque with forces of both vertical and horizontal components. To be in equilibrium, an object has to have no net torque and no net force in either the X or Y direction. So here, if I was trying to figure out what this tension is and what the forces here are, I would set this as my axis. So my torque equation would be V, the vertical component here, times torque in the positive direction, minus H, the horizontal component, times mg, and that equals 0. And once I found out what torque was, the forces in the x direction, fx minus, once I found out what t was, fx minus t will also equal 0, and fy minus mg will equal 0. So here's an example of this sort of problem. You have an 85 kilogram person standing on a lightweight ladder as shown in the sketch. The floor is rough, hence it exerts both a normal force and a friction F1 and a frictional force F2 on the ladder. The wall, on the other hand, is frictionless. It exerts only a normal force F3. Using the dimensions given in the figure, find the magnitudes of F1, F2, and F3. So the weight of the person, this is suggesting you use this axis at the bottom. The person is 0.7 meters from the bottom of the ladder horizontally. The top of the ladder is 3.8 meters vertically. I would use the axis where you have F1 and F2, so they will both cancel out. I'll give you a couple of minutes to work on this. I think I uploaded these slides, updated slides. Let me check. Oh wait, don't turn off the DF2 itself. Let me do that real quick. Because I added a couple of problems. So let me pause sharing, freeze screen, and quickly. It should be updated if I messed up. Resume. Please, I will go through how to solve this problem. Oh, did I not? No, I did. Okay. So A here is 3.8 meters. B is 0.7 meters. F1, F2, and F3 are what we want to find. So, first action. Yeah, it's, no, I missed you. Just wanted to make sure. So, we will be using this point as our zero. So, for torque, force 1 equals 0, force 2 equals 0. mg has a lever arm of b, 0.7 meters. So mg times b, that's the torque from here. And then F3 has a lever arm, a moment arm of 3.8 meters. So minus F3 times A. Except I have those signs backwards. Doesn't actually matter, but let me quickly fix those. This should be minus, and this should be plus, and everything after that is fine. So minus MB, because that's counterclockwise, and that's clockwise, and F3 is turning counterclockwise. So mgb equals F3 times A. So F3 is mg times B over A. So 85 kilograms times 9.81 meters per second squared times 0.7 meters over 3.8 meters gives us 153.6 newtons. So F3 rounds to 150 newtons because everything in this is 2 sig figs. Then we can do the forces in the x direction. In the x direction, oh, that's y. God, these are together wrong. I made a bunch of typos when I put this together real quick. Oops. So force is the y direction. F1 minus mg. equals 0. So F1 equals mg. So F1 equals 85 kilograms times 9.81 meters per second squared, or 833.9 newtons, or 830 newtons. Forces in the x direction, 0 equals F2 minus F3. F2 equals F3, 153.6 newtons, or 150 newtons. So F1 is 830 newtons, F2 is 150 newtons, F3 is 150 newtons. So that's sort of a 2D version of one of these static equilibrium problems. Now let's talk about center of mass and balance. So things balance at their center of mass. So if an extended object is to be balanced, it needs to be supported through its center of mass. And this works out, because torque at the balance point equals 0. And that turns out at the center of mass, m1x, m1g x1 plus m2g x2 equals, where x1 is negative and x2 is positive, equals 0. So you get this balanced situation. So the formula for torque and the formula for center of mass are the same. So this fact that things balance at their center of mass can be used to find the center of mass of an object. You hang it at various angles and trace vertical lines, and those two vertical lines will pass through the center of mass. We did this in the lab on stability. So the center of mass is where the lines meet. So if you dangle something down, we draw a line here, then we dangle it at another point, we draw another line here, and where they meet is the center of mass. So here, for center of mass, where things are balanced here, we're balancing torque. So here, in a balanced situation like this, remember, mass times distance, the force times distance will be balanced on either side. So mass times distance will be balanced. So here's a grade school project. Students construct a mobile representing some of the major food groups. Their completed artwork is shown in the sketch. Find the masses M1, M2, and M3 that are required for a perfectly balanced mobile. Assumes that strings and horizontal rods have negligible mass. So when things are balanced, x1, m1 will equal x2, m2. So this is going to be about building up a set of equations for the various masses and then solving for it. So I'll go through what we can get out of this. So here, torque equals 0. So we get this relationship. M1 times 12 centimeters will equal M2 times 18 centimeters. That means M1 equals 1.5 times M2. That's from this. Now we move on to this. At this point, we have the total mass, M1 plus M2. M1 plus M2 at 6 centimeters equals 0.3 kilograms at 24 centimeters. But M1 is 1.5 times M2. So 2.5 times M2, if we divide 7.2 kilogram centimeters, 0.3 times 24 is 7.2 kilogram centimeters. We divide it by 6, we get 1.2 kilograms. we get M2 equals 0.48 kilograms and M1 equals 1.5 to 0.48 kilograms, which is 0.72 kilograms. And then we can work our way up to this. So here, at 18 centimeters, we have 0.2 kilograms plus 0.3 kilograms plus M1 plus M2. Times 18 centimeters equals M3 times 31 centimeters. But we know what M1 and M2 are, so we can plug those in. 0.72 kilograms plus 0.48 kilograms plus 0.3 kilograms plus 0.2 kilograms times 18 centimeters equals M3 times 31 centimeters. So 1.7 kilograms times 18 centimeters equals M3 times 31 centimeters. So M3 is 1.7 times 18 divided by 31, which is 0.9871 kilograms or 0.99 kilograms. So M1 is 0.72 kilograms, M2 is 0.48 kilograms, and M3 is 0.99 kilograms. So let's talk about more dynamic applications of torque. We talked about static applications of torque. Now let's move on to dynamic applications of torque. Here we get basically Newton's second law. Sum of all torque equals the moment of inertia times angular acceleration. And when we deal with systems that have both rotating parts and translating parts, we have to be careful to take into account all forces and torques. So here, for this falling mass, there is an mg pulling it down, a tension pulling it up, and then for the torque on the pulley, there is a torque causing it to rotate and some moment of inertia resisting that rotation. So here in this situation is the tension in this rope greater than, less than, or equal to mg, and the tension in the rope greater than, less than, or equal to 0. So if you want to work this out, let's look at the mass. Well, mass is accelerating downwards. The force equals mass times acceleration, which equals tension minus mg. Acceleration is negative downwards, so tension must be less than that than mg to accelerate downwards. Oops. I made a spelling mistake. It should be less than instead of less that. I'll fix it after I finish this. So this will have less tension than mg. But if we ask ourselves, is it less than equal to or greater than r? Well, the total torque equals moment of inertia times angular acceleration, which equals minus tension times radius. The angular acceleration exists. The angular acceleration is the acceleration over the radius. So again, acceleration is negative, so tension must be greater than 0 for the pulley to accelerate clockwise. So the tension in the rope is positive. Let me fix my little typo. Man. The general idea is that you have to take into account the moment of inertia and the acceleration of something like the pulley. So now we have angular momentum. So angular momentum, L, is defined as I omega. And using a bit of algebra, we find that for a particle moving in a circle of radius r, L ends up equaling, for a particle, r mv, or radius times momentum. For more general motion, L actually becomes R mv sine theta, or R momentum sine theta. The unit is kilogram meters per second, meters squared per second. Because it's momentum times radius. And angular momentum has some interesting effects, because if we look at I omega, well, unlike mass, mv for momentum, omega, we can change relatively easily. Not omega, I mean I, moment of inertia, we can change relatively easily. And looking at the rate at which angular momentum changes, we find, similar to momentum, we find that sum of all torque equals I alpha, which equals change in angular momentum over change in time. But again, but one of the interesting things with angular momentum is that you can have the angular momentum be conserved, but change the moment of inertia. Let's see. So here, if I have a disk with a moment of inertia of 15 kilogram meters squared, that's rotating at 10 radians per second, what is its angular momentum? Oh, okay, yeah, I'll show you that. Well, moment of inertia is 15 kilogram meters squared. Omega is 10 radians per second. We're looking for angular momentum. Moment of inertia, angular momentum is moment of inertia times omega. So 15 kilogram meters squared times 10 radians per second is 150 kilogram meters squared per second. That's the angular momentum. Now, if the net external torque on a system is zero, the change in angular momentum over time will be zero. Angular momentum will be conserved. And the most interesting consequences occur in systems that are able to change shape. So, time for a demonstration. Oh boy. These work. I happen to be a system able to change shape. So, we start spinning with a large moment of inertia. So I'm applying some torque. This is not the right chair to do it. So I'm applying the torque, build up some angular momentum. I have a large moment of inertia at the moment. If I decrease my moment of inertia, you can see my omega increases. Decreases when I increase my moment of inertia. And now I need to stop, because that demonstration always makes me dizzy. So if you have an object that can change shape, you change the moment of inertia, you cause a change in omega. So, if the mass is out, you have a higher moment of inertia, you switch to a smaller one and you spin faster. And this is something people in sports do all the time. Divers, figure skaters, they use this trick to spin faster. As the moment of inertia decreases, angular speed increases, and so the angular momentum doesn't change. And angular momentum is also conserved in rotational collisions, like dropping a record onto a record player. Record starts out with zero angular velocity. It falls onto the record player base with some angular velocity. The total angular momentum stays the same. So if I have a governing device that consists of two masses of 10 kilograms and a radius of 0.5 meters, you can treat them like point masses. Remember, moment of inertia is m sub I times r sub I squared. Rotating at 10 radians per second. If I then move the masses into a radius of 0.25 meters, what will the angular velocity be? So omega 1 is 10 radians per second at radius of 0.5 meters. Omega 2, we don't know, but it's at a radius of 0.25 meters. I need to sit down and let the nausea free. So mass 1 equals mass 2, and it equals 10 kilograms. Omega 1 is 10 radians per second. Radius 1 is 5 meters, 0.5 meters. Radius 2 is 0.25 meters. Omega 2, we don't know. We'll also need to figure out I1 and I2. So, angular momentum initial equals angular momentum final. So omega naught equals I final omega final. So I equals MI squared. So mass times radius 0 squared plus mass and times radius 0 squared, or 2 mass times radius 0. 2 times 10 kilograms times 0.5 meters squared, which is 5 kilogram meters squared for I naught. I final is going to be 2 times mass times radius final squared, or 1.25 kilogram meters squared. Because 2 times 10 kilograms times 0.25 meters squared. Omega final is going to be I omega naught over I final. So 5 kilogram meters squared times 10 radians per second divided by 1.25 kilogram meters squared. And that will be 40 radians per second. And I should change those subscripts. Any questions? So let's talk about rotational work and power. Well, torques do work. And again, it's an analogy to what you see for linear stuff. So work equals torque times delta theta. Like work equals force times delta x. And the work energy theorem applies as usual. So the change in kinetic energy is equal to the work. And power is the rate that work is done. So power equals torque times omega. This is an analogy to the linear. Power equals force times velocity. So power equals torque times omega. So it takes a good deal of effort to make homemade ice cream. Torque required to turn the handle on an ice cream maker is 4.5 Newton meters. How much work is expended on each complete revolution of the handle? And how much power is required to turn the handle if each revolution is completed in 1.2 seconds? And this is why my ice cream churn is motorized. So torque is 4.5 Newton meters. Theta is 1 revolution or 2 pi radians. Time is 1.2 seconds. We want to find work and power. Well, work is just going to be torque times delta theta, 4.5 Newton meters times 2 pi, or 28.3 joules. And power is just going to be work over time. So 28.3 joules divided by 1.2 seconds, 23.6 watts. And to finish off chapter 11, let's talk about the vector nature of rotational motion. So we've all been talking about rotational motion where everything is sort of fixed in one plane. But reality is three-dimensional. So the way it works out is that the direction of the angular velocity vector is along the axis of rotation of a rotating object. And to figure out the direction of that, if you curl the fingers of your right hand in the direction of rotation, your thumb points in the direction of the angular velocity, the vector for angular velocity. So here, if you have a spinning wheel, you curl your right hand like this, your thumb comes out and points in the direction of rotation. So here, I have Earth spinning away. I don't even know if I'm rotating. But here, if I have my Earth spinning away, and it's spinning in this direction, if I wrap my fingers around, my thumb sticks out along the axis of rotation. If I wanted to describe the direction of omega, it would be along the axis of rotation in the direction of my thumb. So that's sort of the right-hand rule. And then if you have two rotations, you can combine them by adding the omegas. And it also allows you to work out how you add, what happens when you add a torque to something. Because a torque changes the angular momentum. So if you have a torque on a rotating thing, you can get some interesting things like precession, the way that a top wobbles. So a similar right-hand rule gives you the direction of the torque. You curl your fingers in the direction the force is rotating it. That will give you the direction of the torque. And conservation of angular momentum means the total angular momentum around any axis must be constant. This is why gyroscopes are so stable. But it also means when you have something like this, where you have a rotating object, a torque, you get a torque around this axis that will be pulling it down. It combines with the angular momentum sticking out, and it creates a net torque around. And that's how you get the gyroscope doing that wobbling thing. I could probably pull up a short video to show you, but let me just go through the summary at the end of the chapter first. So a force applied so to cause an angular acceleration is said to exert a torque. The torque due to a tangential force is radius times force. Torque in general is radius times force times the sine of the angle. It's often helpful to think of the sine radius times sine of angle as the moment arm. So just how far away the force is from the axis, like perpendicular to it, or you can think about force times sine theta, the component of the force perpendicular to the angle. Newton's second law for rotation is the sum of all torque equals moment of inertia times angular acceleration. In order for an object to be in static equilibrium, the total force and the total torque acting on the object has to be zero. An object balances when it's supported at its center of mass. In systems with both rotational and linear motion, Newton's second law has to be applied separately to each. These are all slightly offset, so let me fix them. There. Angular momentum, L is equal to I omega for tangential motion, That's radius times mass times velocity, or in general, radius for a point object, it's radius times mass times velocity times sine of the angle between the velocity and the radius. Newton's second law is torque equals change in angular momentum over time. And in systems with no external torque, angular momentum is conserved. The work done by torque is torque times delta theta. Power is torque times omega. And rotational quantities are vectors that point along the axis of rotation with the direction given by the right-hand rule. So as an example, let me see if I can quickly pull up a video of a gyroscope processing. Yeah, here's a good image of a gyroscopic precession.
Hey everyone, it's me, Derek, from the channel Veritasium. And I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precession is just one of those things that still blows my mind as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it r. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
So that's this situation, angular momentum is out this way, you add this torque, because again, the right-hand rule, mg is pulling down this way, so the torque is this way. You add this torque to the angular momentum, it moves it around, and then the torque changes direction as it rotates around. And that's why gyroscopes process like that. So that is all for today. We will start up chapter 13 on Wednesday. Yeah, that was the end of chapter 11. Have a nice day. I'm going to